All right, hello. We have day 10 of merit questions for the lead up to these externals, doing one merit question a day. So you've got a whole bunch of resources to go back and have a look at for this merit type of question. Just a reminder that the reason I do it like this is if you're practicing for achieved merit is still useful because the first stages of that will include an achieved question. If you're practicing for merit, obviously you need to do merit questions. And if you're practicing for excellence, a lot of the merit skills are needed for you to then build on and to move on with excellence type questions. Okay, so let's start with this complex numbers question. We've got for what values of p, where p is a real number, does this graph not intersect the y-axis? So what that means is we're looking for a equation that has no real roots. Now that should instantly make you think about the discriminant because that helps us to find types of roots and nature of them. Okay, so let's first of all just unpack what this is telling us. So this is the equation, and we want to think about when it intersects the x-axis. Well, that would happen if px squared minus 4px plus 1 equals 0, because the x-axis is when y is equal to 0. So all I've done there is take this y value and set it to be equal to 0. Now what we want is for there to not be any solutions to that. Okay, so if we've got this equation here and we want there to not be any solutions, then we're talking about when b squared minus 4ac is less than 0. So no real solutions. All right, so carrying on with that, the b part of this quadratic is minus 4p, and we square that. The a is p, and then the c is 1. So I'm just pulling that out from a here, b here, and c here. And we set that to be less than 0. Okay, so this gives us 16p squared minus 4p is less than 0. We can factorize out 4p like this. That's got to be less than 0. So this gives us the values p is 0 and p is a quarter. We just need to figure out which side of 0 and a quarter we're at. So do that by looking at the quadratic that we are looking at in this particular bit is this one here. So that one, if we think about what that looks like, that is a positive parabola. So we have a parabola that's going like this. We've got the x-axis here, and we've just found out it crosses the x-axis at 0 and at a quarter. Now, the portion that we're interested in is when this drops below 0. So for that, it's this section just here that goes below that 0 line, which means that it's going to be anywhere between 0 and a quarter. So our values for p that are going to fit this situation of not giving us any real solutions are anywhere between 0 and a quarter. Okay, now if you're looking for where to get the achieved from that, I'm just going to check the mark scheme and see what we've got. So the achieved came in at this point just here. So that's where you'd get your achieved and then completing it through for merit. Okay, next one we are going to look at is for differentiation. We've got a function given in terms of f of x equals something. We want to know when it's increasing. So think about what this means graphically. If we draw this graph, whatever it might look like, it could be something obvious that's easy to picture. This one's not so easy because it's got that x times log x in it. You could put it into a calculator if you wanted to picture it, but it's not necessary. What we're trying to do though is figure out on that graph, when is it increasing, which means when is it going up? So we're looking for anywhere where that gradient is positive, because that means that our graph will be going upwards. So our first step is to find the derivative of this. So that is when the first term is going to be differentiated into 5. Now the second part, we have a product rule happening. I'm going to do in brackets here just to keep track of my positives and negatives. I'm really terrible at mixing them up. So I just put a bracket around it. Okay, now x log x. We've got u being this part and v being this part. So there's where we're separating our the pieces of the product rule. Okay, so we take the first one and differentiate it. That's 1. And we leave the second one alone. And then we add on, take the first one, but leave that alone, and times it by the derivative of the second one. Well, the derivative of log x is 1 over x. So this becomes 5 minus log x. These x's cancel, and we've got the minus at the front, remember, so that'll be a minus 1. Now, for what values is that increasing? Oh, I can simplify it even more. So we've got 5 minus 1 is 4, so it's 4 minus natural log of x. If we want that to be increasing, we need that to be greater than 0. We need it to be positive. So this will happen when I'm just going to be super careful about my inequality here and really clear on what I'm doing. So if I want to turn that minus log x into a positive, I've got to take it over to the right hand side, which means that then I'm going to reverse the entire thing so that I can carry on working with it on the left, which means the inequality changes over as well. So x has got to be less than, the inverse of doing the natural log is e, so that'll be e to the 4. And just get that ready. If we go to the calculator, I could probably leave it as e to the 4, but I'm going to do that on the calculator anyway. So that would be x, just one moment. Oh gosh, there we go. So I've got too many windows open trying to do this. So x is going to be less than 54.6 to 1 decimal place. Now there is just one small hang up here, and that is that whatever we put in for x has to fit being able to be differentiated. It has to fit this bit here, and the natural log of x, whilst we're saying it's less than 4, we also know that the natural log of x is always positive itself. So you can also pop in here that will be greater than 0 as well, which means that, just one second, which means, losing track, that 0 is a lower limit on that one. So x has to be between 0 and 54.6. That's a hard one to spot at the end there, those limits, but it's looking at this bit here where we've done the natural log of x. We can't have anything that comes out to be negatives because, oh, hang on, should have put this line just here, because we can't put negatives into natural log. If you tried to put in something like, here we go, -4, you'll see you get a math error. So therefore the limits on what we could put into this equation are 0. And the mark scheme did want that specified. This is an old paper, so I have a feeling that sort of stuff hasn't really come up in recent things, but it is something to look out for. Okay, on to integration. So this one is, we've got quite a bit of information here. So I'm going to take a highlighter, which you should take a highlighter into the exam and use as you go through the questions. It's a really good way of getting your brain to notice the important stuff as you go through. So let's start with this hot oven tray is taken from the oven and placed in a room. Now the room has an ambient temperature of 20 degrees. I'm just going to write that in there. So this one here we talk about as being the ambient temperature, which I'll note with temperature and then a little A next to it for ambient, meaning the surrounding temperature. The temperature at which, the rate at which the temperature of the tray changes. So our tray is obviously going to cool down as we take it out of the oven. It will cool down towards 20 degrees. Now it cools down really fast at the beginning and then slower as it gets closer to 20. So what it's telling us in this next line is the rate that it changes at any instant is proportional to the difference between the temperature of the oven tray and the room temperature. So the bigger the difference, the faster the temperature will come down, and a small difference means that that temperature change will slow down. Okay, so the first thing to do is write down a differential equation to represent that situation. So we're being told about a rate. So it's going to be d over d something. We're told the rate at which the temperature is changing, so I'm going to call that a capital T. And that is changing with respect to time, which always gets a little t. Now that is equal to, knowing that it is proportional, means it's equal to a constant times something. And the thing that's being times by is the thing it's proportional to. So that's the difference between the temperature of the oven tray and the room. So that will be the temperature of the tray, which we've called the capital T. That's the bit that we decided on here. So the temperature of the tray is our capital T. And we are going to take off the temperature of the room to find the difference between them. Okay, we've set up our differential equation, and now we're going to move on and use it to work out some stuff. So we're told the temperature of the oven tray is originally 220 degrees. So when T equals 0, the temperature of our tray is 220. After 3 minutes, the temperature is 100 degrees. So when T is 3, capital T is 100. Now we've got enough information to solve the differential equation and then use it to work out the last piece of this, which I'll just do in another colour to make it stand out so we don't forget it. So then we will find out what the temperature of the oven tray will be after 2 more minutes. So that will be when T equals 5. So we've had 3 minutes already, and it's going to be 2 more minutes after that, so T is 5. All right, let's get stuck in. So let's start with well, actually, I'm not going to write it again. You've got it there at the top of the screen. But what we'll need to do is separate variables. So we bring all of the capital T over to the left side, and dt goes to the right. So we have 1 over capital T minus 20 dt. The k stays where it is, and we bring the dt up to the right. That means we can integrate both sides. So if we integrate 1 over capital T minus 20, then we have the natural log of T minus 20. On the right hand side, differentiating k with respect to t is kt plus c. So then if I want T minus 20, and remember our aim here is to get some equation in T, so that's why I'm unpacking what's happened to T. So we would do e to the kt plus c. Now that is equal to, just using our laws of powers, that would be the same as saying this. Now e to the c, well, e is a constant being raised to the power of a constant. So it's better to just write that as one constant. It still is just a constant that we haven't worked out yet, which means that we can put it at the front here and we get AE to the KT. So then T is equal to AE to the KT plus 20. Okay, now we've got two constants we don't know. We've got the A and we've got the K, but we've also got two sets of information that we can use to work it out. So from the first one, when T is 0, we get the temperature was 220, AE to the 0 plus 20. Well, e to the 0 is 1. So 220 is A times 1 plus 20, so A must be 200. Okay, now using the other bit of information. When T is 3, then we have the temperature was 100. We have, let me just move that slightly, there we go. AE to the KT plus 20, but now we know that A is 200, so we can put that in there. The T is 3, so that becomes 3K. So now working that through, I'll do 100, take away the 20 first of all. I'm just conscious to keep checking in case anybody needed some help here. Right, now divide by the 200. So I'm at the point where I've got e to the 3k is equal to 0.4. So now if I take log of both sides, I'll get 3k is equal to log of 0.4. So k is a third log of 0.4, and I'm deliberately not turning that into a decimal at this point because I know I'm going to go on and use it in the next step, and I want it in a form that's easy to just plug straight into the calculator and it be fully exact. Right, so back to the original temperature equation. All right, so now what I'm doing is, actually let's just switch up the colors so we can track this. So the equation that I've got here, I'm going to put all of the values into that. So T is equal to 200. We worked out that K is 1/3 natural log 0.4 times T plus 20. And the question asks us to work out the temperature it will be when T is 5. So if T equals 5, we're going to have 200 e to the 1/3 natural log 0.4 times 5 plus 20, and over to the calculator. I'm going to need to put in some brackets here. Just go back and do that. In fact, I'm going to start over. I'm not going to do it all in one line because I don't trust that the brackets are going to work out. Okay, so I'm going to put it a piece at a time. So log of 0.4, then divide it by 3, then times it by 5, raise it to the power of, raise it so it's the power of e, times by 200, add on 20. And we get T is equal to 63.4 degrees C. Units weren't entirely necessary for the end there, but you have them in the question, you may as well give them. And the achieved on that one, I'll just go and check where that was. That was getting the correct differential equation, correct general solution after the integral. Okay, so achieved was down here. So getting the equation to begin with up here. We needed that to then carry on with and do the first stages of the integration without solving for the constants. Okay, those are our 3 questions for today. Took a little bit longer today than the last couple of ones have done. We've done 3 of them in 20 minutes, which is still really not bad going. If you multiply that across 3, because you need 3 merits on each paper for a merit overall, then you're talking about an hour, and you can have merit done across all 3 standards, with plenty of time to spare to then go on and give the excellences a go. With the ones that I did today, these are pretty standard questions, and it was really that last one that takes a little bit longer because there's so many pieces to work out, but the other 2 I don't think were too bad. Okay, I'm going to leave it there. I will be back again tomorrow to add another merit or set of 3 merit questions, 1 per standard, to our collection, so you can use those for your revision and study. I'll pick out the questions that I'll put into tomorrow's video and put them onto my Instagram story, so you can take a look at them ahead of time if you want to see if you can do it first and then join in with my solutions tomorrow. Tomorrow I think I will be on at about 6 p.m. So yeah, you can come join me live or you can watch it later, and hope that helps.